What is accuracy? Accuracy is the hardware store. Accuracy is the true value of a quantity. What does that mean? Accuracy is the number of significant figures, or sometimes called significant digits. True value of a quantity is never known. You may think that a meter stick is exactly 1 meter long, but how long it actually is depends upon the manufacturing process. If we want to know what accuracy is, we need to know what the number of significant figures is. We have to know what a significant figure is. A significant figure is reliably indicated by the measuring instrument. What does that mean? One and only one estimated digit is significant. No more, no less. Example of what we mean by a significant figure or a reliably indicated figure or digit. For any measurement, the final digit is considered to be the estimated digit. For example, here we know that the length of the pencil is somewhere between 6 and 7, whatever the unit is. So to estimate this quantity, we would say 6. That's definitely reliably indicated. And then perhaps 0.2. We cannot go any further than that. The 2 is reliably indicated. This has an accuracy of 2 significant figures or digits. Here we have more graduations. And so to estimate this figure, to read this instrument properly, we can see 6.5, 6.6, 6.7, but not 6.8. Here we get a blow up. And so we estimate we have 10 fingers, we have 10 toes, we can think in tenths. We estimate, let's say 6.7 and perhaps 8. Therefore, for this reading, we have 6.78 where the 8 is an estimated digit. This measurement has an accuracy of 3 significant figures. Reporting significant figures. Zeros are significant in 3 cases. One is if the 0 is marked, another is if the 0 is between 2 significant figures, and the third is if the 0 is a trailing decimal 0. Non-zeros, such as 1, 2s, and 3s, are always significant. Let's do some examples. 200 with the decimal place is 3 significant figures. 200 without the decimal point, that is only 1 significant figure. Those zeros trail, but they are not trailing decimal zeros. 200.0, that is 4 significant figures. The third 0 is significant because it is a trailing decimal 0. The other 2 zeros are significant because they are between 2 significant figures. 3,500. Those 2 zeros trail, but they're not trailing decimal zeros, so here we have 2 significant figures accuracy. 3.050. This 0 is a trailing decimal 0. It is significant. This 0 is between 2 significant figures. It is significant. 4 significant figures. 700,000. Technically, these are trailing zeros, non-decimal, and so only the 7 is significant, 1 significant figure. 0.007. This 0 is just for emphasis. You don't even have to write it. And it is a leading 0. These 2 zeros, they are decimal zeros, but they lead. They do not trail. So we only have 1 significant figure. 20,001. These zeros are between 2 significant figures, and so we have 5 significant figures. 0.0020. This 0 is a trailing decimal 0. It is significant. These are not 2 significant figures. 6,200,000. 2 significant figures. 1.0020. This 0 is a trailing decimal 0. It is significant. Here we have 5 significant figures. 801,300. These zeros are not significant. Therefore, we only have 4 significant figures. Accuracy is the number of significant figures. but precision is the place value of the least significant figure, something entirely different. 6.42 centimeters has an accuracy of 3 significant figures, but the least significant figure is the 2, and that has a place value of 1/100th of a centimeter. Therefore, the precision of this reading is 1/100th of a centimeter, where the 2 is an estimated digit. Now let's talk about how we round calculations. If we only add or subtract, then we round to the least precise number that is used. But if we multiply or divide, which is almost always, the rule is different, we then round our calculation to the least accurate number used, which is the fewest number of significant figures. For example, example 1, a substance has a mass as measured on a balance scale of 8.72 grams and a volume of 1.1 cubic centimeters as measured by a graduated cylinder, 2 different instruments. What is the mass density of the substance, rounded to the appropriate number of significant figures? Mass density is the mass divided by the volume. In this case, 8.72 grams divided by 1.1 cubic centimeters. We put that in our calculator, we get 7.92727 repeating on and on grams per cubic centimeter. But since we have obviously divided here, we cannot report all these extra digits. We have to round to the least accurate number used, which is an accuracy of 2 significant figures of 1.1 cubic centimeters. Therefore, we round to 7.9 grams per cubic centimeter. However, if we're to use this calculation for further results so as to not propagate round-off error, we would use all the available significant figures. Let's compare accuracy and precision. Demonstration problem 2, which of the following measurements is the most accurate and which is the most precise? Part A, 0.005 millimeters. Only the 5 is significant, so the accuracy here is just 1 significant figure. The least significant digit is the 5, and its place value is 1/1000th of a millimeter, and so that becomes the precision. Part B, 0.050 meters. The accuracy here is 2 significant figures because this is a trailing decimal zero. It is significant while this one is not. The precision is this place value, which is 1/1000th of a meter. But to compare apples to apples, since the other 2 that we're looking at are millimeters, we must convert that to millimeter. 0.001 meter is 1 millimeter. Part C, 600.0 millimeters. The accuracy here is 4 significant figures because this 0 is a trailing decimal zero. You would not write it were it not significant. So we have an accuracy of 4 significant figures here. Precision is the place value of this 0.0, which is 0.1 millimeters. Now to answer the question, which of these following measurements is the most accurate and which is the most precise? We see that the most accurate measurement is the 600.0 millimeters at 4 significant figures, greater than 2, greater than 1. However, 600.0 millimeters has a precision of only 0.1 millimeters. Now revisit the question of which of these measurements is the most accurate, which is the most precise. We see that 600.0 millimeters is the most accurate at 4 significant figures, but its precision is only 0.1 or 1/10 of 1 millimeter, making it the least precise of all the numbers. However, 0.005 millimeters, while it is the least accurate of the measurements, is the most precise at 0.001 millimeters. Consider demonstration problem number 3. Here we measure with 2 different instruments supposedly. With the first instrument we get 1.16 meters, and with the second instrument we get 3.7 meters. And so we need to add these numbers. So we do that. And when we do that, we get 4.86 meters. However, here we've only added, and therefore the rule becomes round to the least precise number or to the place value of the least significant digit used, least significant figure used. And so that means since we only have the nearest tenth of a meter with this number here, we have to round our answer to the nearest tenth of a meter as well. And so that gives us 4.9 meters as a result. Now it is your turn to work some problems. Enjoy.